Hello, we have here a table lamp whose base is 12 cm long. The base of the lamp is quite heavy, it weighs 15 newtons. The lamp itself is only 15 newtons. The lamp has a flexible stem, and let's assume that the weight of this stem is negligible compared to the weight of the base and the lamp. The question is, how far can we extend this lamp before the lamp topples? Since the lamp is going to topple about this point here, we are going to take moments about this point, the right extreme end of the base. So the anti-clockwise produced by the 15 newtons, so 15 times 6 cm, must be balanced by the clockwise moments produced by the 5 newtons force. So 5 newtons times, let's call this distance x, alright? So 5 times x. So turns out we can extend the lamp a distance of 18 cm beyond the base before the lamp topples. So solving this problem is actually not difficult, but I would like to discuss further how the normal contact force changes as we shift the lamp further and further away from the base. Let's start by positioning the lamp right above the middle of the base. So when the situation looks like this, we know that the total weight of the lamp, which is 5 plus 15 newtons, should be supported by a 20 newton normal contact force. And the 20 newton contact force should act at the middle of the base. When we shift the lamp away from the middle of the base, the normal contact force must remain as 20 newtons because we still need 20 newtons of upward force to support 20 newtons of weight. The line of action of this normal contact force, however, cannot remain at the middle of the base. Let's take moments about the point here, the middle of the base. Then you realize that both the normal contact force and the weight of the base exert 0 moments about this point, whereas the 5 newton force exerts a clockwise moment. If this is indeed the picture, then the base is no longer in rotational equilibrium because there's a net clockwise moment about this point here. This means the 20 newtons normal contact force must have shifted to the right of the middle of the base. This is so that the normal contact force can now produce an anti-clockwise moment to balance the clockwise moment of the 5 newton weight of the lamp. What do we mean by a shifting normal contact force? Now remember, the normal contact force actually does not act at one single point. The normal contact force is actually the resultant of many normal contact forces acting at every point along the base. So if the normal contact forces are equally distributed, then it is equivalent to one single 20 newton normal contact force acting at the middle of the base. If the normal contact force are leaning stronger towards the right, then it is equivalent to a 20 newton normal contact force that's not at the middle of the base but more to the right of the base, which is the situation here. If we take moments about the middle of the base, then we can write this equation here. So the anti-clockwise moment 20 times A must be balanced by the clockwise moment of 5 times B. Clearly, as we increase B, as we move the lamp further and further away, A must also increase, which means the line of action of the normal contact force will also shift further and further away from the middle of the base. So why does the lamp topple eventually? It must be because the line of action of the normal contact force has already reached the furthest end of the base already. So this is the situation here. The normal contact force has already reached the end of the base. At the beginning, when we solved this problem by taking moments about x, were you aware that the normal contact force is actually there, the 20 newton force is actually there, but it just doesn't feature in this equation because its line of action was lying at point x as well. It's not that there was no normal contact force, it's just that it exerts 0 moment about point x. Okay, that's all. Ta-ta!